I want you to picture something for a second. Just imagine you were standing right at the edge of this massive, breathtaking canyon.
Oh, yeah, like a really immense drop.
Exactly. You're looking out over this immense chasm, right? Just staring down at these sheer rock walls that plunge, so far into the earth. They look like they could just swallow entire mountains whole.
Right. It's a very humbling kind of view.
It really is.
Yeah.
And as you're standing there, just like taking in the sheer scale of it, you're faced with this really jarring reality.
Yeah.
That massive void was carved by a river.
Yeah. The water did all that work.
Which is crazy to think about. It's the exact same unhurried flow of water you could happily, paddle a canoe on.
Yeah.
So, okay, let's unpack this. Because staring at a mile of empty space that used to be solid rock, I am really struggling with the physics of it.
I mean, that's a very natural reaction.
Right. Because water is yielding, it's soft, rock is hard. How does a peaceful stream physically crack open the earth?
Well, the mistake we make is looking at water through the lens of human time. If you only observe a river for, a few decades, water is just water. It seems gentle. But to understand how it cuts a canyon, you have to introduce deep time.
Deep time. Meaning like millions of years?
Millions upon millions of years, yeah. When you apply deep time to the equation, rivers cease to be just bodies of water. They become these relentless geological engines.
Even with millions of years, though, I mean, water flowing over solid granite feels like it should just polish the rock, maybe? Like make it slippery?
Yeah, you'd think it would just kind of glide over it.
Right. It doesn't feel like it should be able to literally saw a mile down into the crust. So what is the actual physical mechanism doing the cutting?
So it comes down to kinetic energy, basically, and what that energy carries. If we travel up to the factory floor, so to speak, the birthplace of the river high up in the mountains, the water isn't just flowing, it's falling.
Because it's so steep up there.
Exactly. Gravity is pulling it down incredibly steep gradients, and that steepness converts the water's potential energy into raw kinetic energy. And that energy fuels this physical process called hydraulic action.
Okay, hydraulic action. I've heard that term. But what does it actually look like on, a microscopic level? Is the water just hitting the rock with a lot of force?
It goes much deeper than just surface impact, actually.
Oh, really?
Yeah, so as water surges turbulently over a riverbed, the sheer pressure of the current forces water and bear bubbles deep into tiny microscopic fissures in the bedrock.
Oh, like into the tiny cracks in the stone itself.
Right, and then when the water rushes past and recedes for just a split second, the pressure suddenly drops. So those trapped air bubbles rapidly expand and they literally explode outward.
Wait. So the river is essentially using high-pressure air pockets to blast the rock apart from the inside?
Exactly. It is a continuous series of micro-explosions happening like millions of times a day.
That is wild.
Yeah. And over time, that hydraulic action pries the bedrock apart. But that's really only the first phase.
There's more.
Oh, yeah. Once those fragments break off, the mechanics get much more violent. The river captures those broken pieces of mountain, and they become its physical tools.
Okay.
Which brings us to the next major mechanism, what we call abrasion.
Okay, I always picture abrasion like heavy-duty sandpaper. Like the water is just dragging grit and gravel along the bottom to grind away the bed.
What's fascinating here is that the sandpaper analogy is a good starting point, but it's really more like a sandblaster combined with a jackhammer.
A jackhammer. Okay, that's a violent image.
Well, geologists categorize a river's cargo. We call its load into different types. The heavy materials, the large stones and boulders, they make up the bed load.
Right, because they stay on the bed of the river.
Exactly. But because the water is moving so fast and turbulently in the mountains, these heavy rocks don't just slide nicely along. They get picked up by the current, carried forward, and slammed back down against the bedrock.
So they are actively hammering the riverbed as they travel downstream.
Yes. It's a process called saltation. They bounce and they smash. They smash into the bedrock and they smash into each other, shattering into smaller and smaller pieces as they go.
Wow.
A mountain river is literally sawing its way down into the earth using the earth's own fragmented stones as the teeth of the saw. The mountain provides the exact ammunition required for its own demolition.
Okay, that completely changes how I look at a mountain stream now. Like, it's not just a peaceful brook, it's a high-speed, self-sustaining demolition site.
That's a perfect way to describe it.
But mountains don't go on forever, right? I mean, eventually the river descends out of the highlands, the steep slopes soften, the landscape flattens out into plains.
Right, the gradient totally changes.
So when that gradient drops, what happens to all that kinetic energy? Because, physics says it can't just vanish.
No, the energy doesn't vanish, but its application fundamentally shifts. Up in the steep mountains, gravity dictates that the river's main job is downward erosion.
Cutting that deep V shape into the earth.
Exactly. But once it hits the flatter plains, it loses that aggressive downward momentum. So its primary job shifts from eroding to transporting.
Right, it has to move all the debris it just blasted out of the mountains.
And moving that cargo is a monumental task. We mentioned the bouncing bed load, but the river is also carrying a massive suspended load.
Suspended load, so that's the stuff floating in the water.
Yeah, these are the fine particles of like silt and clay that swirl in the current. It's actually what gives lower rivers that cloudy, kind of muddy look.
Oh, okay, like the Mississippi or something.
Exactly. And beyond that, there is the dissolved load.
Wait, dissolved?
Yeah.
Like salt in water.
Right. Minerals chemically leached from the rocks. Totally invisible to the naked eye, but it represents thousands of tons of material moving downstream.
So out on the plains, the river basically transforms into this massive geological conveyor belt.
Exactly, a giant conveyor belt.
But this is also where the shape of the river completely changes, right? Like it stops running in a straight line and starts carving these broad, sweeping loops that geologists call meanders.
Yep. Meandering is a classic feature of flatland rivers.
I've always wondered about this, actually. If the ground is totally flat, why doesn't the water just take the shortest, straightest path to the ocean?
It seems like it should, right? But when you look at fluid dynamics, a straight line is actually incredibly unstable in nature.
Really? Unstable?
Yeah. When a river hits flat ground, any minor obstacle, like a slightly harder patch of clay, a fallen tree, an uneven bank, it will deflect the flow of water just a fraction of a degree toward one side.
Huh. So a tiny nudge creates a slight curve. But how does a slight curve turn into a massive, miles-wide loop?
It comes down to centrifugal force and shear stress. Think about being in a car taking a sharp turn at high speed.
Okay, you get pressed hard against the outside door.
Right. Water does the exact same thing. As the river enters that slight curve, the centrifugal force pushes the fastest, most energetic water against the outside bank of the bend.
Which means that outside bank is taking the absolute brunt of the river's energy.
It takes massive shear stress, accelerating erosion on that outer edge, but the physics on the inside of the curve are totally different.
Because the water is slower there.
Exactly. Because the fastest water is pushed outside, the water on the inside of the bend slows down dramatically, and when water loses velocity, it loses its ability to carry sediment.
Oh, I see.
So it starts dropping its suspended load right there on the inner bank.
Got it. So it's aggressively chewing away the outside bank while simultaneously dumping new land on the inside bank.
Yes. And there is a fascinating three-dimensional dynamic driving this, too. It's called helicoidal flow.
Helicoidal flow, what does that mean?
Well, as that fast surface water crashes into the outer bank, it gets forced downward toward the riverbed. It scrapes the bottom, sweeps across the channel, and spirals back up toward the inner bank.
Wait, so the water isn't just moving forward, it's moving in a continuous corkscrew shape down the river channel.
A literal corkscrew, yes. This helicoidal flow acts like a vacuum. It sweeps the freshly eroded dirt from the outside bank, rolls it across the riverbed, and neatly deposits it on the inside bank.
That is amazing.
It creates a permanent feedback loop. The outside pushes further out, the inside fills further in. Over thousands of years, that tiny initial deflection exaggerates into a massive, sweeping meander across the floodplain.
And sometimes those loops get so extreme they actually cut themselves off.
They do, yeah. As the meander loops wider and wider, the neck of land between the two curves gets narrower and narrower. Eventually, usually during a major flood, the river will just break straight through that narrow neck.
It just takes the shortcut.
Right. It takes the steeper, more direct path and completely abandons the old loop. That abandoned curve of water is left behind as a crescent-shaped lake.
An oxbow lake.
Exactly, an oxbow lake.
So by looking at a river valley from above, seeing all the sweeping curves and the scattered oxbow lakes, we're essentially reading a physical record of fluid dynamics trying to balance energy across a flat landscape.
Precisely. The shape of a river is a readable history of its energy state.
I love that way of framing it.
Yeah, a straight, deep channel tells you gravity and downward cutting are dominating. A wide, wandering channel surrounded by oxbow lakes tells you lateral fluid dynamics and sediment transport are running the show.
Here's where it gets really interesting to me, though. All of this material, The bed load, the suspended silt, the dissolved minerals, it's all riding this conveyor belt.
Unstoppably moving downstream.
But this process can't go on infinitely, right? Eventually the river reaches the ocean. The conveyor belt has to stop.
And this introduces the river's third great geological job. We had erosion, we had transportation, and now we arrive at deposition.
Drop in the cargo.
Right. As the river meets the sea, the flat topography and the sheer standing mass of ocean water act as a massive hydraulic brake. The river's velocity plummets almost instantly.
And because carrying capacity is tied to velocity, the river simply drops whatever it's holding.
It drops it in a very specific, sorted order based on settling velocity.
Oh, so it doesn't just dump everything all at once.
No, it's very organized, purely by physics. The heaviest sands and gravels fall out of suspension first. Then the finer salts settle. Finally, the lightest clays are carried furthest out into the salt water before they slowly, eventually, drift to the bottom.
But because it's dumping so much solid material in one centralized place, the river actually starts choking on its own cargo, doesn't it? Like it builds a roadblock out of its own sediment.
It does. It fills in its own channel until the water is basically forced to spill over the banks and branch out into dozens of smaller diverging streams called distributaries.
Right, distributaries.
And this continuous dumping and branching fans out into that iconic triangular shape we call a delta. The river is literally building entirely new land masses out into the ocean.
I was thinking about this earlier, and it is a total mind bender. Like if you follow the logic of everything we just assessed, the hydraulic action in the mountains, the transportation across the plains, the deposition at the coastal delta isn't just a swampy pile of mud. You are looking at a dismantled mountain.
That is the profound reality of deep time.
It's just wild.
You are looking at the pulverized remains of distant highlands, reassembled grain by grain at the edge of the sea.
Wow.
Given enough millions of years, rivers will not just carve deep canyons, they will erase entire mountain ranges down to sea level.
But hold on, that brings up a massive contradiction, I feel like.
Oh, how so?
Well, the Earth is billions of years old. If rivers are constantly grinding the land down and washing it into the ocean, why aren't the continents completely flat by now? Why do we still have the Himalayas or the Rockies?
That is because the Earth's surface is trapped in a permanent staring contest.
A staring contest.
Yeah, on one side you have the exogenous forces, water, ice, gravity relentlessly trying to flatten the world. On the other side you have endogenous forces, plate tectonics.
Ah, right.
Deep inside the Earth, massive crustal plates crash together, buckling the surface upward to forge new, towering mountain ranges.
So the tectonics push the crust up into the sky, and the rivers immediately start attacking it to bring it back down.
It is a permanent state of tension. Every gentle rolling hill you drive past used to be a jagged peak, and every jagged mountain you see today is currently in the process of being leveled.
That puts things in perspective.
Yeah, the scenery outside your window is just a frozen snapshot of an endless, slow-motion war between tectonic uplift and river erosion.
So what does this all mean for us? Because, this endless geological war isn't just ancient, abstract history. It directly created the environment human beings rely on to survive.
Oh, absolutely.
We basically built our entire civilization right in the crossfire of this process, particularly when you look at floodplains and deltas.
Human civilization owes its existence to river deposition, frankly.
Really, its existence.
Without a doubt. Because the river is grinding up rocks from the mountains, the sediment it carries is packed with essential raw minerals. When a river meanders and naturally floods its banks on the plains, the water slows down and drops a fresh layer of this fine, mineral-rich silt across the land.
It's essentially delivering premium fertilizer straight to the soil.
Exactly. Which explains why the Nile, the Tigris, the Mississippi, almost all great human civilizations and our most productive agricultural zones are located right on top of active floodplains.
Because we desperately need that rich soil to feed ourselves.
Yes. But this creates a massive paradox.
Right. We need the soil that floods create, but we build our cities on these plains, and human beings cannot tolerate floods.
Exactly. And the human response to that paradox has always been engineering.
We try to fight the river.
We try to isolate it. We build massive concrete levees, dams, and artificial embankments to lock the river into a single, permanent, predictable channel. We stop the water from spreading out so we can protect our homes and our crops.
Let me push back on this strategy, though, because looking at the physics we just talked about, it feels fundamentally flawed. flawed.
Oh, it has massive unintended consequences.
Right, because if a river's natural mandate is to erode, transport, and deposit, and we build concrete walls so it can never deposit its load on the floodplain,
Yeah.
where does all that sediment go? It doesn't just vanish.
If we connect this to the bigger picture, it goes exactly where you'd fear, and the consequences are devastating.
Oh, no.
By walling the river in with levees, we force the water to stay deep and move faster. It acts like a fire hose.
A fire hose of mud.
Yes. Instead of naturally spreading its sediment across the delta over time, the river shoots all that sand and silt straight out the mouth into the deep ocean.
So we are completely starving the delta of new land.
We are starving it. And deltas are incredibly heavy geological structures.
Because of all the mud.
Exactly. And without fresh layers of sediment being constantly added by seasonal floods to build the land up, the sheer weight of the existing mud causes the land to compact and physically sink.
Wow.
Geologists call this subsidence.
Wait, so by building levees to protect coastal cities on a delta, we are actually causing the ground underneath those cities to physically sink below sea level.
Look at New Orleans and the broader Mississippi River Delta. The Mississippi is one of the most heavily leveed and engineered rivers on the planet.
Right, they have levees everywhere down there.
And because the delta is completely cut off from its natural resupply of sediment, the land is subsiding at an alarming rate. It is sinking into the Gulf of Mexico.
That is tragic.
It is. Ironically, our engineering to prevent localized river flooding has made the entire region infinitely more vulnerable to catastrophic oceanic flooding from hurricanes and sea level rise.
It really sounds like we're just picking a fight with millions of years of geology. Can we ever really tame a river with concrete long term? Or is it a fight we are guaranteed to lose?
When you measure time in centuries rather than, fiscal quarters, geology always wins.
Geology always wins.
Always. Sensible land and water management requires understanding fluid dynamics and respecting the deep time mandate of the water. We cannot just plug the exhaust pipe.
So what's the alternative?
Managing flood risk sustainably means giving the river room to spread out. It means designing designated floodways where the river can safely deposit its load and rebuild the land without destroying communities.
We have to work in tandem with the engine.
Exactly. You have to work with the natural process, not against it.
That is a completely different paradigm for how we view our infrastructure. Like, we have to stop seeing the river as a pipe we can route and start treating it like a living geological force.
That's beautifully put.
Next time you cross a bridge over a river, I really want you to look down at the water. If it's got a brown tinge to it, if it's murky and turbulent, realize you aren't just looking at dirty water. You are watching the land itself. You are watching a piece of a mountain from hundreds of miles upstream traveling, grain by patient grain to the sea.
This raises an important question, though, and it's a thought I'd love to leave you with today.
Oh, please do.
We talked earlier about that grand tension between the Earth pushing up and the rivers tearing down. Plate tectonics act as the engine pushing mountains into the sky, and rivers relentlessly wear them away.
Right, the ultimate staring contest.
Right. But what if the Earth's tectonic engine ever just stopped?
Stopped, like complete.
Yeah, I mean, the core of our planet is slowly cooling. If billions of years from now, the deep heat dissipated and the tectonic plates stopped colliding, there would be no new uplift. No new mountains would ever be born.
Wow, how cool.
But the sun would still shine and the rain would keep falling. The water would keep flowing.
Oh, wow. Because the erosion engine is powered by solar energy and gravity, not the Earth's internal heat.
Exactly. So if uplift permanently stopped, would these patient, gentle rivers just keep sawing and transporting? Would they eventually wear every single continent perfectly flat until the entire solid landmass of Earth slipped quietly beneath a shallow, global ocean?
A perfectly smooth underwater world, all because the rivers never, ever stopped working. That is a haunting and beautiful image. Definitely something to mull over the next time you're out paddling a canoe. Thanks for diving deep with us today.